So welcome to today's lecture in the FJelinekSeries. Today we have Deyi Xiong from, as you see, Externality University, but in fact Deyi was at different place until very recently at Suzhou University, and before 2013 was actually 6 years in Singapore. And I got interested, in fact, well, first of all, he visited us when we were working on the QTD project in Portugal. So since Martin is not here, but some other people already met Deyi there. And in fact, I got interested even more when I saw one of his papers at Coding this year. So we decided to invite him, and he will talk about incorporating knowledge in the neural machine translation. So please.
So thank you very much. Yeah, to invite me here. It's my great honor to be here. So I'm going to talk something personal on today's neural machine translation. So not-based machine translation is not new term. I was part of the master century. Then come out the code-based machine translation because it's take time to construct non-based or non-based machine translation. So during the last 20 years, we can see a much progress has been made for statistical and neural machine translation. And in this year, I think some companies even argue that the performance and neural machine translation reached the human parity. So does that mean the data solve everything for machine translation? Maybe a lot. So here I show some examples. So this example 2 English sentences we want to translate from English to Chinese. So the only difference is in the preposition phrase. The first one is in the last linear, the second one is in 10 minutes. Okay, so we use Google Translate, online translate, to English sentences into Chinese. Maybe you don't understand Chinese, okay? So I translate this Chinese translation back to English. Then you can see what's wrong with these translations. So the second one is okay. It's when you translate back from Chinese translating to English, it's the same as the original source sentence. But the first one is completely wrong, right? It's especially for the prepositional translation. So we can see that the reading procedure lasts for 1 million years. So that's impossible, right? Okay, we also apply another online translation engine that's developed by a Chinese big company. So this is a translation again for the 2 English sentences to Chinese, and we translate back into English. So the first sentence, the translation for the first sentence is okay, but the second sentence we can see the in 10 minutes is translated into 10 minutes later. So you can see the problem with the preposition phrase translation. So here the real problem is the preposition phrase, like in the last million years or in 10 minutes, what they should be attached to, like the verbal read or the long evolution. So this is I think it's easy for human beings because we have some common sense or word knowledge in like the read cannot, the procedure of reading cannot last like a million years, but the evolution can, right? So we can easily attach the million years to the evolution and come into read. But for machine, it's quite difficult because they lack of this word knowledge or common sense. So why this happens? So let's look at this channel from the human brains to data and to empty model. So human brains like aware of storing a huge amount of linguistic knowledge and word knowledge. So based on this linguistic knowledge and the word knowledge, we can speak, we can write, right? So this spoken language and written language then are collected as language data, and based on this language data, we train machine translation model. But when we compare the trained machine translation model and human brains in terms of the knowledge, you can find there is a huge enough gap in the empty model and the human brains. So that's the reason that the machine sometimes it's not practical for them to attach the preposition phrase correctly. So why this happens? So we look at this channel from the human brain to language data, then to empty model. For each step in this channel, you can see some not to loss. So since we cannot collect all the data that human beings speak or write, right? So we only collect a very small portion of this data. So in order to reduce the knowledge loss for this step, maybe we can collect more language data. And for the second step, from the language data to the empty model, we can also see sometimes the model just is not able to learn anything and everything in the data. Because sometimes, due to the complexity of training time, we have to do some substance, substance. And this substance actually limit the capacity of this model. So for this, maybe you can make our model more expressive in order to reduce the learning loss during this step. So are there any other ways to incorporate knowledge into empty models? So for traditional knowledge-based machine translation, you can see actually we use some methods to maybe help somebody to real language base to help improve the quality of machine translation. But this process is time-consuming and expensive. So for neural machine translation, if we want to incorporate knowledge into model, here I think I will say 3 ways to do this. The first way, we can to allocate the knowledge with the data. So the data is allocated with explicit knowledge. For this method, like the knowledge augmentation and the data level. And the second way, we can directly incorporate the knowledge into the neural machine translation model. So this is like a model level knowledge augmentation. And the third way, we can directly build some submodels in our neural machine translation. And this submodel will help that machine translation model to mine some knowledge that knowledge was not able to be used by the original neural machine translation models. Okay, so what kind of knowledge can be used for neural machine translation? So here I roughly divided this knowledge into 2 categories. The one category is the internal knowledge. It's also from the community of deep learning, they call it doc knowledge. That's knowledge learned by the model from the data. And this knowledge is sometimes naturally compatible with the neural models, but it's not quite friendly to human beings because we cannot understand that's knowledge embedded in the neural machine translation model. And the second one is external knowledge. So this knowledge actually is a knowledge that cannot be learned by the neural machine translation model, but they do exist in various forms. So we can see a lot of forms for this external knowledge. So there can be the sentence level linguistic knowledge, called syntax and syntax, something like that. And also can be the discourse level linguistic knowledge, like the discourse relations or reference. And it can also be domain-specific knowledge, like the bilingual terminology bank. And this knowledge can also be translation fragments. These fragments show how something how this some phrase, basic phrase like idiom, how they can be translated into other language. And it can also be the prior knowledge indicating some constraints for machine translation, like the discourse reading, coherence, and translating consistencies. So you can see the externality and useful for machine translation actually exists in a very great variety of forms. They are not limited to the quantity or graph. Okay, so how can we use this to conduct knowledge to improve neural machine translation? So we can explore the internal knowledge for neural machine translation. I think this is a very interesting direction because currently we see some work on this. So basically, this knowledge we can use like a knowledge transformer, tune the models or domains of languages. So you using some parameter sharing or multitask learning. So this is I think there are some interesting work on this topic. But today I'm only focused on the second kind of knowledge, external knowledge. So for external knowledge, just as I mentioned before, here there's two ways to explore external knowledge in neural machine translation. The first one is data level knowledge implementation. So basically we annotate the data with some specific knowledge, and then we train the neural machine translation model on this data annotated with knowledge. And the second one is the model level augmentation. So for this, we just build a knowledge base. Then we develop a new model, or maybe change the neural machine translation model to allow them to freely access to this knowledge base. So this is basically the outline of this code. So it has two parts. The first part is the code level, data level knowledge augmentation. The second one is the model level augmentation for neural machine translation. So let's first look at the first part. So in this part, I will introduce our two works recently done for to explore this external syntax knowledge for neural machine translation and the external domain knowledge for neural machine translation. So let's look at the first one, the modern source tag in neural machine translation. So why do we need to incorporate the syntax knowledge into neural machine translation? So here I give two examples. It's from Chinese to English. So this, in the first example, the long phrase 新生银行 in Chinese actually should be translated into, into English counterpart as an entire unit. But in this example, you can see the NMT actually translated this phrase into two parts and separated by another translated in technical side. So that's completely wrong. For the second example, we can see the long phrase two girls translated twice in the technical language. So we hope maybe if we know this phrase or long phrase, you can put some syntactic constraints on this translation of this phrase. So that's basically what we want to do. Since I'm interested only in the source syntax, so here we only do some work on the encoder of the neural machine translation. So for each source sentence, we now have a word sequence. Then we use a parser to generate the passphrase for this source sentence. I think it's difficult to directly incorporate the passphrase into neural machine translation. So here we use some phrase, or we linearize the passphrase according to the discourse-level. So for each word sequence of the source sentence, we can obtain a linearized sequence. We call this sequence as a structure-level sequence. So once we have these two sequences, actually, then we have two encodes for each source sentence to the neural machine translation system. Then we propose three new encoders to incorporate these two sequences. So the first one is a simple one to call the parallel RNN encoder. Actually, we have two encoders, separate encoders. One for the original source sentence, and the other one for the structural level sequence. Then we can calculate, the embeddings or representations and learn from these two encoders together. Then we use this representation to guide the decoding of the decoder. So the second one is hierarchical RNN encoder. For this, we first build RNN encoder for the structural level sequence. Then on this RNN, we again stack another RNN encoder for the source sequence, word sequence. And the third one is quite straightforward method. We just use the mixed sequence. We use an encoder to encode the mixed sequence with also word sequence and words and structure labels. So that's basically what we've done here to incorporate the two sequences into NLP. So let's look at the experiment results. We have some experiment results on Chinese to English. And you can see here, for each of these three methods, we have obtained some improvements over the baseline. The parallel encoder achieved about 1 blue point improvements, and the hierarchical one achieved about 1.1 blue points. And the baseline is the mix R achieved 1.4 blue points over the baseline. So I think these improvements are reasonable because you can see the mixed one is the base one, and better than the hierarchical one, and better than the parallel one. The reason for this may be that so for these three methods, we actually have some encoders. These encoders encode the source sequence, source word sequence, and the structure data sequence. And for these two sequences, there are some interactions in the encoders. So for the first one, actually we have two separate encoders. So the interaction between the word sequence and the structure data sequence maybe is not that strong. But for the hierarchical, it's stronger than the parallel one. Then for the mixed one, actually we only use one sequence. And in this sequence, there are words and structure labels. So the interaction between the words and the labels are actually very strong in this method. So we guess that's the reason for this improvement achieved by these different methods. Okay, we also conduct some analysis on this method, these four aspects. So the first one is we are interested to investigate the effects on non-sentence translation. Because for Chinese to English translation, the non-sentence translation is very challenging. It's very challenging. Sometimes this is because it's due to the divergence of the discourse-level. Because in Chinese, sometimes we have a very long sentence. Actually, it's a compound sentence. Like these sentences consist of very short sentences separated by the commas, and then this separate sentence, like a sub-sentence, actually should be translated into a single English sentence. So that means one sentence in Chinese can be translated into a multiple sentence in English as a discourse. So that's the difference for Chinese to English translation. Also cause a lot of challenges to translate non-Chinese sentences into English. So here we just conduct some analysis to combine. This method can help help neural machine translation on the non-sentence translation. Okay, for the word alignment, actually we use some false decoding, and then we have some test sets, and on these test sets there are some human, the manual word alignments. So we compare the manual word alignment with the word alignment generated according to the teaching ways in neural machine translation. So we can see calculate the average error rate. So we can see that our method actually substantially decrease the error rate for the word alignments. Then for the phrase alignment, as I mentioned in the examples, so the first example, the noun phrase, actually the translation of the noun phrase is interrupted by anti-translation in the text side, right? So that means that the phrase is not translated as a whole unit into the text side. So here we just check these situations in our test sets. So we can find our method can actually indeed improve this situation. So we look at the different categories, syntax categories. You can find for the long phrase, PP phrase, you can see the rate and the ratio of long continuous translations actually decrease. And for the continuous translation, the ratio is increased. So you can see our method can also help the problem that we mentioned before. Okay, for the overtranslating, that means, for neural machine translation, there are two very serious problems. One is we call it the overtranslation. That means some phrases or some words are repeatedly translated. And the other one is untranslated. So these two problems are actually related to the coverage. But here we can see our measure can also help this. So we just propose a matrix to evaluate how serious of this problem. So this ratio actually is related to the number of times of words repeatedly translated in the typing language. So we can see here the mixed RN can decrease the ROT. That's the ratio of the overtranslation from the 5.5 to 4.5. So that means our method can indeed help this overtranslation problem. So that's the first work that we done on the data label application, and you can see that syntactically can be helpful for neural machine translation. So for the second work on this topic, you can use the domain-specific knowledge to improve neural machine translation. So why we are interested in domain-specific knowledge? Because in many specific domains, some phrases or some words have their own ways to translate. For example, like in the e-commerce domain, there's I think like the eBay, Amazon, or like the Chinese company Alibaba, they are quite interested to translate e-commerce domain web page from English to Chinese or Chinese to Russian. And for this domain, there are many specific terms. They have their own ways to translate. You cannot translate in different ways, otherwise it can cause some problems. So we want the neural machine translation to translate in the way that we want it to translate. So the basic idea, we just build a bilingual database to store the translation for these specific terms. Then we want the neural machine translation to use the translation of these terms. So the challenge here, there's two challenges for incorporating the bilingual lexicon into NLP. The first one is that this bilingual lexicon actually are like a symbolic knowledge. They have symbolic representations, but for neural machine translation, they work on continuous representations. And the second one is some phrases will actually have multiple word translations. But in neural machine translation, the decoder is running word by word fashion. So there are two challenges to incorporate this symbolic bilingual lexicon into neural machine translation. So what we do here actually is a very simple but effective method to do this. We either change the model nor the decoding algorithm. So we see some previous work on this that either change the model or change the decoding algorithm. Here we do nothing. We just annotate the training data with the knowledge from the bilingual lexicon. So for example, like here, we have some phrase like long sock in Chinese. First we tag with 2 marks for this phrase on the beginning and the ending of this phrase. Then we use the target side to replace the source side in the source sentence. So we can see here we are using these tags. So then for each instances in our training data, we retrieve our bilingual listing database to see if there are any entries already in the database. If there are translation for some phrase, then we use this phrase to tag the source part of this source sentence and replace with the phrase translations. So the reason that we do this is because we believe that the neural machine translating and the neural network has very strong capacity to learn some patterns. So we just give some signals to allow them to learn these patterns, like tagging. So based on the tagging, we want to the encoders to learn this tag phrase should be translated into an entire unit into the tagging translations. So that means these words inside these two marks should be translated together, not be interrupted by other translations. And by sharing, then we use the tag side word embedding to replace the word embedding of the source words. So this will give some signal for the neural machine translation to learn that these two phrases in the source side and tag side should be aligned to each other. So basically we use this tag and sharing and allow the neural machine translation to learn their translation correspondence. Okay, so this some results on Chinese English. So if we use the tagging, we have some improvements. If we use both tagging and sharing, we achieve the basic performance. And then we also take a deep look into the data. You can see that for baseline, only less than 70% of these phrases are translated by the baseline system. But if we use this training method, we can improve the accuracy from the less than 70% to 95%. So this method is simple, but it's quite effective on incorporating the domain-specific technology into neural machine translation. Okay, let's look at the second part. It says this part is focused on the model level knowledge of application. So here
Maybe can we ask questions for the first part now, or should we wait?
Of course we can.
Yeah. So I was curious whether you have tried also some like baselines or. So my question was for the approach where you were augmenting the input with some additional syntactic information, actually linearized as part of the input of the neural entity system. Whether you have also tried some dummy tags or some fake information, because we have tried various setups similar but different underlying structure.
You mean the first syntax-based method?
And we have seen improvements by adding simply false information, random tags and other things. And the underlying reason is that by simply making the input longer, we train the network in a different way and therefore better and it performs better. So we have seen improvements for the wrong reasons. And I was curious whether you also saw, whether you validated this in some
So you mean you use a sequence that's longer than the original one and actually hurts the performance?
Yeah, so we did power speech tagging and also some syntactic tags, and instead of inserting the true tags, we inserted random tags. So obviously there was no linguistic information in the random tags, and still the blast scores increased.
Okay. Yeah, sometimes I difficult to get the real reason for the improvements. But here we actually do some analysis to. We take deep look into the syntax categories to see what really happens. I think this maybe is the real reason for the improvement. But for your case, I don't know the real reasons for the improvement. Sometimes maybe you have more data, or sometimes maybe you use a larger level or something like that. that will also improve the performance.
So I just want, it's possible that it works in your case, but we saw improvements for the wrong reason. So I think it's again more important to not only evaluate like the improvement against the baseline and your approach that has some extra information, but also against some like dummy benchmark where you formally make it similar, but do not provide the real information that you are claiming to be helpful.
Use some like random
random text,
something like that.
damaged linguistic information, and you have to see no improvement from this damaged information to be sure that it comes from the source that you assume it comes from.
Yeah, I think that's it's a problem. it's difficult to interpret how the improvements come from. Sometimes, for the back translation, actually we know that it will introduce some noise, but it still improves the performance.
So it's your analysis could be really valuable. You can see improvements in word alignment, but still they can come from the wrong reasons. That's a different question.
I don't think so for our case. Actually, it's indeed from the technology that we incorporate into the system. Because we actually don't have down on several aspects, not only only one aspect. And from these four different aspects, we actually have some, they are coincident, they are incident with each other and show the problems. Okay, so for the second part, is on the model level. For this, we actually also have some work on like modeling coherence and coding big translation memory into machine translation. So first of all, modeling coherence for neural machine translation. This actually is done for like discourse-level, document level neural machine translation. So we can see the sentence level neural machine translation, the quality for sentence level actually is getting better and better, but at the document level, we can see a lot of problems, like the consistency, disarticulation, and coherence. So that means that on the document level, there are a lot of information maybe not used in neural machine translation. So here we want to incorporate this discourse-level knowledge into neural machine translation. Here we propose a neural cache model. So in this model, there are three parts. The first part is there's a cache, something that to store some recently translated words or some words related to the topic of the entire document. And the second part is a metric to evaluate the entries in these two caches. And the third one is how to integrate this cache model into neural machine translation. So I will go through the details one by one, but very briefly. Okay, so for the dynamic cache, actually, this cache used to store the words from recent translations. And this cache appeared in a first in, first out fashion. So that means we have some size for the cache. And this cache will we keep only both the recently translated 50 words something. And so for duplicate entries in this cache actually are removed. Okay, for the topic cache, it's different from the dynamic cache. Dynamic cache it actually is keeping changing and changing, but the topic cache is once the document is given, the topic cache actually fixed. So here we use the title words from the topics, but for the source document during the testing, we don't have the topic words. I mean the topic word on the title side. So how do we do this? We actually use LDA to learn the topic word for the source document, and also train another LDA to learn the topic word for the tag document. Then we train some mapping function to learn map from the source topic word to the tag topic words. So during the decoding, we have the topic word for the source document. Then we use this learn mapping function to translate the source topic words into the tag topic words. Then we store this mapped target words in the topic cache. Then we combine these two caches together and use the same word images that we use in neural machine translation. So since we have this cache model, then we also have the decoder in neural machine translation. They will generate the tag words. So how do we evaluate the words in this cache? So that means how good are these words maybe according to the context. So here we just use some neural networks to evaluate the probability for the words in the cache. We use some like the hidden state, previous words, current words, something like this, and combine them into a neural network. Okay, so once we have the probability for what entries in the cache, and then we want to combine the probabilities with the probabilities estimated by the neural machine translation decoder. So here we use a gating mechanism to combine them together. So that's widely used in a lot of work. So here so this work actually present in Colin, I'm not sure if student since present this work. So actually this work has been done 2 years ago. So we still use RNC as our baseline. So here we can see if we use the dynamic cache, we can have some improvement about 1.5 over the baseline. And if we use the dynamic cache and the total cache together, we have more than 1.5 improvement on the baseline. So we actually have some analysis on the translation of the text set. We find that this cache model can improve the lexical coherence. But here we don't show these results. Okay, so for the final, the last one, that's also deep on the model level to incorporate externality into neural machine translation. So this time we incorporated the entire translation memory into NMT. So why we do this? Because we have sometimes we have some collaboration with human translation company. In human translation company, they normally use translation memories. So because they always translate some documents, and this document actually the translation can be reused. And according to some statistics, they found that more than 70% of their previous translation can be reused. So how can we combine the translation memory with neural machine translations? So normally the translation memory is like private data, so we cannot access them, so we cannot use them as the training data to train neural machine translation. But the human translation company want to use the neural machine translation system. So they want this MD system can be accessed to their translation memory on the fly. So basically, we want to allow the neural machine translation system to do this. So here we introduce some change to the traditional encoder-decoder NLP system. So for the encoder, we actually have two encoders. So one encoder is to encode the original source sentence, and the other one is used to encode we here call it the match translations. So for each source sentence to be translated, we will retrieve on the machine translation memory to find the most similar translation to the current source sentence. So then we use these match translations here, and then use a separate encoder to encode this match translation. So you can imagine that the one encoder for the source language and the other encoder for the target language, and our decoder will generate a word in the target language. So the encoder, this encoder is for the target language. So you can imagine they have a very big impact on the decoder because they are in the same language, right? So in order to balance the impact of the additional encoder, we clearly again use the gating mechanism. So for each encoder, we have the attentive mechanism for them. So for the encoder of the source sentence and the decoder, we have attentive mechanism to have some translation correspondence relations. And then for the TMT encoder, we also have some attentive mechanism to connect this encoder with the decoder. So the decoder know which part should be reused. So for the other part, maybe not much to the translation memory, then this part will be translated by the traditional part of the MT system. So that's the formula, just scaling. Okay, so here we show some general results. So the first column we show the 5D match score for the match translations is measured to estimate the similarity of the match translation to the source sentence. So, but in our experiment, actually we use the sentence embedding to calculate the similarities. But we want to compare with following the traditional ways in previous work. Here we show the 5 match scores. So the second column shows the result from the baseline, and the third column results for the gated translation memory augmented neural machine translation. And the last column in this table actually shows the follow scores for the match translation memory. So we can see here, if the 5 match score is higher than 0.5, then the incorporation of translation memory into neural machine translation can help a lot. The higher the 5 match score, the higher improvement you can obtain. For example, in the first group, from the 0.9 to 1, in this group we can see the translation memory can achieve about more than 30 blue points improvement. So that's indicates that the translation memory actually can be very helpful to incorporate.
So if I may again interrupt with a question. I see. Well, first question is it's pretty interesting that the MFS score is so perfect that just half is the good dividing point. Like I don't know the MS score, like what exactly how it is designed, but you have the two sources, the original corpus and the original source and the translation memory candidate, like with the same weight, kind of, or modally sized for their weight, but it matches with the split, the half split of your score.
Maybe due to the ways that we build our data set, actually we have like 1,000 676 test sets, and for each group of these test sets, we have exactly the same number of test sentences.
Yeah.
So that will be the reason for, you can see it's higher than 0.5 improvement, short improvement, and lower than 0.5 no improvement.
Yeah. And then I was also curious about the ends. So if you are in the very high interval, it would actually be better to disable neural empty whatsoever and simply use the translation memory. And on the other hand, if the score is very low, it would be better to like this rely on
That's the board, the translation memory.
That's the translation memory. So I was wondering whether this is the planned setup so that you would still like skew the ends and use it, because this score, the MFS score, is available only once you have the reference translation, or do you have it beforehand?
Actually, yes, this fundamental score can be, I think, can be calculated on the fly, but in our experiment we don't use any fundamental scores. We just to get the translation memory and
but for an end user system,
these scores.
But for the final system, you could calculate the FMS score, and if it's higher than the threshold, you would simply return the translation memory match, and if it's lower than the threshold, you would forget translation memory.
I think it's a can be done. Okay, so conclude. So here we talk about the knowledge and the data and the neural machine translation. You can see the knowledge is very important for machine translation, but in data-driven or corpus-based machine translation, like statistical machine translation and neural machine translation, actually there are a huge knowledge gap in the models and the human brains. So here we can see the two kinds of knowledge, the internal knowledge and the external knowledge. External knowledge actually exists in various forms, and this knowledge can be incorporated into neural machine translation with different ways. But in this talk, actually, I have to say something about the internal knowledge. This is also very important, and I think it's a very interesting direction, because for this, everyone knows that neural machine translation is difficult to understand, difficult to interpret. So this part, I think, maybe you have to understand how the neural machine translation organizes internal knowledge in neural networks. Then we maybe can find a way to transform between the internal knowledge and the external knowledge. So I think it's maybe an interesting future work. So the final words, so we can see for the machine translation research, they have two paradigms, like the rule-based and the knowledge-based and the corpus-based. So we can see lots of progress made by the corpus-based machine translation, but maybe there are some limits for this research paradigm. So we have to look back to see how linguistic knowledge can be used to improve machine translation. So here we actually want to promote a data and knowledge-driven machine translation paradigm, not only purely data-driven machine translation research paradigm. So this is a reference for this talk. Okay, thank you very much.
Okay, so thank you very much for the talk. And now we have time for even more questions than just objects. So anyone else? Yeah, sure. I don't want to forbid you to ask any question.
Thank you. So, the next question that I had is a broader one. Based on the title of the talk, I was kind of expecting, maybe wrongly, I was anticipating that you would talk about world knowledge as well. And all the knowledge that you have mentioned so far is in some point like linguistic, either it's linguistic annotations or it's the knowledge which is available in the previously translated text of translation memories. Do you have, you or other colleagues in your department have also some enterprises that would include the word knowledge?
Yes, yes, quite interesting. We mostly focus on linguistic knowledge, but as we shown in the example, actually, word knowledge is kind of like non-linguistic knowledge is also very important. But it's very useful to incorporate this knowledge, but also it's very difficult, it's challenging to incorporate such word knowledge because we don't have a word knowledge base. And I know some groups working on these topics, but I think it's quite in a very emerging stages. I think for the future, it's definitely a direction to explore.
So maybe it may work, or it may be easier to access in some very limited domains.
Yeah, I think
where you are already recording some data from some whatever, clever sensors or whatever, so that you know that the temperature is never higher than something, and by that you can somehow like forbid some mistranslation of that. So it could be limited to very specific domains.
Yeah, that may be possible. So in traditional knowledge-based machine translation, so people just construct some knowledge-based by, and they actually use all the like linguistic knowledge and word knowledge in one knowledge base. But I think it's maybe better to separate these two kinds of knowledge, and then we have some like spatial base for the word knowledge. So for very specific domain, that may be possible. So actually, we talk about the incorporating the bilingual based only to neural machine translation. We can store that word knowledge as a kind of in the bilingual based or something like that. As maybe for the translation of specific terms, maybe it's related to the word knowledge or something. So, yeah, and just like external knowledge, there are very many different ways for word knowledge to represent, to exist, to model. So, yeah.
Anyone else? You have motivated the use of the translation memories by saying that sometimes people cannot give the memory publicly or make changes to data. But so what if you would simply retrain the system on the translation memory?
Yeah.
And not include anything else? When would how would that work?
Yeah, that's a good question. We actually thought about this after we published these papers, I don't remember the results. I think it's maybe if you just train on the translating memory, that's more good as train on like the calculation of the translation memory with your training data. So. But if you train on both the translation memory and training data, definitely you have some improvements. But that's not the way for the human translation company they want to do, because they don't want to use this data. They don't want to give this data to you, so you cannot have access to them.
Okay, any other questions? Okay, so I think we are at time, so the hour is over. So we thank you once more again. So thanks for your talk.
Thank you.
It concerns the next program. You may have noticed that next Monday we have the discourse-level talk in the afternoon. It's within a kind of workshop which we had with our French colleagues. The morning program of the workshop is filled by the Czech participants, and the location is Carolinum, one of the lectures.